In this video, we're analyzing an inelastic collision between a point mass and an extended rigid body. So our point mass is a blob of clay with a mass of 400 grams moving 3.5 meters per second. And this slams into the tip of a rod that has a mass of 2 kilograms and a length of 1 meter. Now this rod is hinged on a smooth bearing at the top. And after the collision, the combined masses are going to rise to some maximum angle, which is the ultimate goal of the problem. Find that maximum angle. So to quickly summarize some of the big ideas in this problem. First, energy is not going to be conserved in the collision itself. Just like any other inelastic collision, there's going to be energy lost. What is conserved is angular momentum. And we know this because there's no external torque acting on the system at that moment. It's just the two objects exerting torques on each other. So angular momentum is conserved in the collision. Now, once that's over, we're going to switch to talking about energy conservation. So immediately after the impact, we have some amount of rotational kinetic energy, and then this is smoothly transformed into gravitational potential energy as the combined masses rise to that maximum angle. Even the potential energy calculation itself is somewhat complicated because we have a rigid body involved. So the gravitational potential energy of the point mass, that's pretty straightforward. But then for the actual rod, we're going to have to track the height of the center of mass of the rod in order to figure out its gravitational potential energy. So to get started, in part A, we're asked to compute the angular speed of the combined masses immediately after the impact. So the rod is still oriented vertically. It hasn't started to rise yet. We're just doing the inelastic collision. So just starting from first principles here, it's a conservation of angular momentum problem. So we have L initial is equal to L final. And our initial angular momentum is all in this point mass that's just moving along with a translational velocity of 3.5 meters per second. And this thing does have angular momentum with respect to this rotation axis at the top. And I'll post a link to the video where this was first derived. I did a video on the angular momentum carried by a point mass moving along in the translational sense. And the way this turned out is that the angular momentum is given by the momentum, mv, and I'll use a little m for the clay blob, times the perpendicular lever arm length, or the distance between the point mass and the rotation axis when it's at its minimum distance from the rotation axis. Well, that's just equal to the length of the rod itself. I'm going to use a capital L for that. So there's the initial angular momentum carried by this point mass, and that's equal to the final angular momentum of both objects stuck together and rotating. So then our final angular momentum is given by I omega, so the total moment of inertia times the final angular velocity. And that moment of inertia has two different pieces. There's the point mass, which has a moment of inertia normally that we would call mr squared, but the distance to the rotation axis is L in this case, so little ml squared, plus the moment of inertia of the rod itself. And the moment of inertia of a rod is going to be 1/3 times its mass, and I'm going to use a capital M for that, times the length squared, so L squared again. So there's our total moment of inertia, and then our final angular speed we'll write as omega final. So one of these L's is going to cancel out. I divide one of them out of the right-hand side. And we're going to solve for omega and then just try to clean things up algebraically before we put numbers in. So omega final is going to be mv in the numerator, and then we have to divide by this term in parentheses. So while I'm doing that, I'm going to go ahead and factor an L out of that term. And so I end up with L times little m plus 1/3 big M. Now there's one more thing that's nice to do here algebraically before we put numbers in. I'm going to get rid of the complex fraction. So I'm going to multiply the top and bottom by 3. And so I get a 3 little mv divided by L times the quantity 3 little m plus big M. So now we can plug in the numbers. And in the numerator, I have 3 times the mass of the clay blob, that's little m, that's 0.4 kilograms, converting from grams there. My initial speed, 3.5 meters per second. The length of the rod, 1 meter. And then 3 times little m, so 3 times 0.4 plus big M, which was 2 kilograms. And when I run the numbers on this and just keep a little extra precision here, I end up with 1.313 radians per second. Okay, so that's the angular speed of the combined masses after the impact using angular momentum conservation. Now the whole combination begins to rise, and we're going to convert the rotational kinetic energy into gravitational potential energy. So again, just rewinding all the way to first principles, E initial is equal to E final. As this thing rises under the influence of the conservative force of gravity. So in our initial state, that's all rotational kinetic energy. So it's going to be 1/2 times the total moment of inertia times this omega final squared. And note there that the omega final is actually the initial angular velocity for the energy conservation process. And then in the final state, it's all gravitational potential energy, but this has to be split into two parts. I'm going to call it U for the clay plus U for the rod. So we can get the total moment of inertia into the equation easily enough. We've already seen this once before, so it's ml squared for the point mass, that's the clay blob, and then a 1/3 big M L squared for the rod times our angular velocity, which we call omega F squared. But things get tricky when we get into the gravitational potential energy. So for the clay blob, if we just start there, we're implicitly going to call the lowest point in the problem y equals 0 for that guy. So it starts with 0 gravitational potential energy, and we don't have to worry about that. And we have to figure out how much higher it is in the final state and relate that to theta max. And this is a really common trick with a variety of pendulum type problems. If I take L times the cosine of theta max, it gives me the length of this vertical line segment. So that piece is L cosine theta max. But the distance from the hinge all the way down to the y equals 0 point, that's L. And we're looking for this little difference between those 2 points. That's going to be L minus L cosine theta max. So that's how we write the final height of our clay blob. So I end up with mg times the final height, which is L minus L cosine theta. And I can factor an L out of that and write this as mgl times 1 minus cosine theta max. Now for the rigid body itself, the gravitational potential energy depends on the change in height of the center of mass. And I'll post a link to the video where that was first derived. So this time, the 0 of our coordinate system will be chosen as the original location of the center of mass. And then we just use the same trick that we did for the clay blob. The length from the hinge to the center of mass, that's L over 2 because this is a uniform rod. And we're interested in finding the final height of that center of mass. And we build this right triangle with a hypotenuse of L over 2. And that means the length of this segment is L over 2 cosine of theta max. And that means this little change in height is L over 2 minus L over 2 cosine theta max. So it's basically the same trick, just with half the length. So then for the final gravitational potential energy of the rod itself, I'm going to go ahead and pull the 1/2 out in front. So I have 1/2 big M G, and I'm going to pull the L out of there. So there's L times the quantity 1 minus cosine theta max. So note that we have this common factor on the right-hand side of 1 minus cosine theta max. Ultimately, we want to isolate that so we can solve for theta. So I'm just going to go ahead and write that now on the left-hand side, and we'll clean everything else up over to the other side. So I'm going to try to do actually a lot all at once here. So I want to clear out all of these fractions, the 1/2s and 1/3, by multiplying both sides of the equation by 6. This leaves me over on the original left-hand side, which is now our right-hand side, with a 3 little m L squared plus big M L squared. Just noting there that that would have had a 1/6 in front of it, but we multiplied both sides of the equation by 6. And that's all multiplied by omega final squared. And then in the previous line on the right-hand side, we have these two terms, little mgl and 1/2 big M GL, added to each other, and the 1 minus cosine theta max part has been factored out. Now multiplying these by 6 and then dividing them out, I end up with a 6 mgl plus a 3 big M GL. Now note, one of these L's is going to cancel, and I'm just going to move that big equation at the bottom over to the left to make some room here. And now we can plug in our numbers. So I end up in the numerator with 3 times 0.4. Remember, 0.4 is the mass of the clay blob. And I'm going to go ahead and factor out the L as I'm working here. So then I end up with plus big M, which is 2 kilograms, and I factor the L out, that's 1 meter. And then I put in omega final squared, which is 1.313 radians per second, and we're squaring that. In the denominator, I have 6 times 0.4, and I'm going to factor the G out as I'm working, plus a 3 times big M, which is 2 kilograms. That quantity, all multiplied by G, that's 9.8. And when I run the numbers on this, I get 0.067. Now we still have to solve for theta max. And you can do this all at once in your calculator. So what I'm imagining here is adding cosine theta max to both sides, and then I subtract 0.067 from 1, and then I take the inverse cosine of that. So I do 1 minus 0.067, hit enter in the calculator, and then do the inverse cosine of that result, and we get a final angle of 21.1 degrees. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.